Every drop of oil you have ever burned, every gallon of jet fuel that has lifted a plane across the Atlantic, every ton of diesel that moves a VLCC tanker across the oceans, every plastic device in your hands right now, it all began with this: a single-celled organism floating in an ocean that existed hundreds of millions of years before the first dinosaur walked the earth. It lived for a few days at most, drifting on currents, feeding on sunlight, and then it died. It sank through miles of dark water. It settled on the seabed. And there, buried under unimaginable weight and heat, across geological time scales the human mind was never designed to comprehend, it became something else entirely. This is the story of how the earth made oil, and how that process created the $100 trillion foundation of the modern world. I am Chris, the maritime economist. To understand crude oil, you have to understand something that most people never pause to consider. The Earth has not always looked anything like it does today. 180 million years ago, during the Jurassic period, the planet was almost unrecognizable. The continents were fused into a single landmass, surrounded by warm, shallow seas. Carbon dioxide levels were 4 to 5 times higher than they are today. The planet was a hothouse, and those warm, nutrient-rich oceans were teeming with life. The life in these ancient oceans was overwhelmingly microscopic: phytoplankton, zooplankton, algae. Trillions of individual organisms, each one a tiny factory converting sunlight into organic carbon. They lived fast, died young, and sank. Here is the first critical condition for oil formation. You need an enormous volume of organic material, far more than the ocean's natural decomposers can consume. And in the Jurassic and Cretaceous periods, the conditions were perfect: warm temperatures, high nutrient runoff from rivers, low oxygen zones on the seabed where dead organisms could accumulate without being eaten by bacteria or scavengers. This is the second critical condition. You need rapid burial. When those plankton died and sank to the seabed, they did not simply rot away. They were buried continuously and by new sediment: sand, silt, clay, the carcasses of larger marine creatures. Year after year, millennium after millennium, the organic rich layer grew thicker and thicker. Eventually, it was hundreds, sometimes thousands, of feet deep. The organic material in this layer was now trapped, cut off from oxygen, cut off from the decomposers that would normally break it down. It was no longer rotting, it was cooking. This is where the third and most crucial condition comes into play: temperature and pressure. As the organic rich sediment was buried deeper and deeper by the weight of accumulating rock above, it entered what petroleum geologists call the oil window. This is a very specific depth and temperature range, roughly 2,000 to 5,000 meters below the surface, at temperatures between 60 and 120 degrees Celsius. Inside this window, something extraordinary happens. The complex organic molecules, the lipids, proteins, and carbohydrates that once made up living cells, are broken down by heat and pressure into simpler hydrocarbon chains. This process is called catagenesis, and it takes millions of years. Too shallow, and the organic material never gets hot enough to transform. It remains as kerogen, a waxy precursor to oil. Too deep, above 120 degrees Celsius, and the oil itself breaks down further into natural gas, primarily methane. The oil window is narrow, and the Earth has to keep the source rock inside it for millions of years for a commercially viable deposit to form. This is why oil is not everywhere. It is why it is concentrated in specific geological provinces: the Middle East, the North Sea, the Gulf of Mexico, West Africa, the Caspian Basin. Those regions had the three conditions simultaneously: enormous organic productivity, rapid burial in a sedimentary basin, and exactly the right depth and temperature maintained over geological time. But crude oil does not stay in the source rock where it was born. It moves. Here is the fourth condition for a viable oil deposit: migration. After the oil is generated, it must travel from the source rock, which is typically a fine-grained, low-porosity shale, into a reservoir rock where it can be stored and eventually extracted. The mechanism is simple physics. Oil is lighter than water, and the source rock, after millions of years of compaction, is under immense pressure. The combination of buoyancy and pressure squeezes the oil out of the source rock, like water being wrung from a sponge, and forces it upward through whatever permeable pathways it can find. This migration can take the oil tens or even hundreds of kilometers from its birthplace. It moves through porous and permeable rock layers, typically sandstone or limestone. It moves upward, driven by buoyancy, and it keeps moving for millions of years until it hits something that stops it. Anticlinal trap, a dome-shaped fold in the rock layers. Oil migrates into the dome and is trapped by an impermeable cap rock above. Fault trap, a fracture in the rock where a permeable layer has been displaced against an impermeable layer, creating a seal. Salt dome trap, a plug of buoyant salt has pushed up through surrounding rock layers, creating traps around its flanks. Stratigraphic trap, a change in rock type, a sandstone lens encased in shale, or a reef buried in impermeable sediment. A trap is exactly what it sounds like, a geological formation that catches migrating oil and holds it in place. There are four main types. The most common and the easiest to find is the anticlinal trap. Imagine a layer of porous sandstone folded into a dome shape, sealed above by an impermeable cap rock. Oil migrates up into the dome and cannot escape. It accumulates. Over millions of years, billions of barrels can fill a single anticline. Fault traps occur when geological forces fracture the rock and displace one side against the other. If the displacement brings a permeable reservoir rock against an impermeable seal, the migrating oil is stopped. Salt dome traps are common in the Gulf of Mexico, offshore West Africa, and the Persian Gulf. Salt is buoyant. It rises through surrounding rock over geological time, deforming the layers around it and creating traps along its flanks. And stratigraphic traps are the most subtle and often the most rewarding. They are not structural at all. They occur when the rock type itself changes. A sandstone channel cutting through shale or an ancient coral reef buried in marine sediment. The oil is trapped not by folding or faulting, but by the geometry of the rock itself. Every major oil field on Earth, every billion-barrel discovery, every supermajor basin exists because these five conditions aligned in one place at one time across hundreds of millions of years. Organic rich source rock, rapid burial, the oil window, a migration pathway, and a trap. The Gawa field in Saudi Arabia, the largest conventional oil field ever discovered, with an estimated 70 to 100 billion barrels of original oil in place, is a massive anticlinal trap. The Permian Basin in Texas combines multiple trap types across stacked reservoir layers. The Niger Delta is dominated by fault traps formed as the delta sediments collapsed under their own weight. The conditions had to be perfect, and for the largest fields, they were. Now, let me give you the single most important number in this entire series. The oil that humanity extracts today, the crude that powers our ships, fuels our vehicles, and feeds our petrochemical industry, was formed from organic material deposited between roughly 400 million and 65 million years ago. Most of it falls in the Jurassic and Cretaceous periods, a window spanning about 130 million years. Human civilization has been extracting oil at industrial scale for roughly 160 years, since Colonel Edwin Drake drilled the first commercial oil well in Pennsylvania in 1859. In that time, we have burned through roughly half of the conventionally recoverable oil the Earth spent hundreds of millions of years creating. Read that again. The Earth produced oil across a span of more than 100 million years, roughly 500 times longer than the entire history of the human species. And in less than 2 centuries, we have consumed half of it. This is why oil is not a renewable resource, not in any meaningful sense. The processes that created it, the plankton blooms, the sedimentation, the burial, the cooking, are still happening today. The Earth is still making oil right now in sedimentary basins around the world, but it is making it at a rate measured in milliliters per century. The rate at which we consume oil is roughly 10 million times faster than the rate at which the Earth can produce it. You could wait 1,000,000 years and not get back a single year of current global consumption. This is not a moral argument. It is not an environmental argument. It is a geological fact. The oil under your feet is a one-time inheritance, a planetary savings account that was deposited over hundreds of millions of years and is being withdrawn in a geological heartbeat. Every barrel you pump today is a barrel that will never be replaced, not in your lifetime, not in your children's lifetimes, not in the lifetime of the human species. Now, you might be wondering why I just spent 15 minutes explaining plankton, source rocks, and geological traps from 100 million years ago. Here is why. Everything you touch, nearly everything you own, consume, or depend on exists because of the 5 conditions I just described. The phone in your hand contains plastics derived from crude oil. The clothes on your back, if they contain polyester, nylon, or spandex, are petroleum products. The food you eat was grown with fertilizers made from natural gas. harvested by diesel-powered machines and transported in diesel-powered trucks and ships. Roughly 65 to 75% of every barrel of crude oil is refined into transportation fuels: gasoline, diesel, jet fuel, marine bunker fuel. But the remaining 25 to 35% becomes petrochemicals, plastics, synthetic rubber, solvents, lubricants, waxes, asphalt, and from those petrochemicals, the supply chain branches into over 6,000 distinct consumer products: 45% gasoline, 25% diesel and heating oil, 10% jet fuel and kerosene, 7% petrochemical feedstocks, ethylene, propylene, butadiene, 5% LPG, propane, butane, 3% heavy fuel oil, marine bunker, 5% asphalt, lubricants, waxes, solvents. Each fraction then branches into its end uses, a sprawling web of products. That petrochemical stream, just 7% of each barrel, produces the ethylene that becomes polyethylene, the most common plastic on Earth. It produces the propylene that becomes polypropylene, used in everything from car bumpers to medical syringes. It produces the butadiene that becomes synthetic rubber for tires. It produces the benzene and xylene that become pharmaceuticals, dyes, and electronic components. There is no substitute for crude oil in these applications, not at scale, not at cost. The global economy runs on oil not because it chose to, but because nothing else comes close to its energy density, its transportability, and its versatility as a chemical feedstock. And this is where SeaMayors enters the picture. Every day, roughly 60 million barrels of crude oil move across the ocean in tankers, VLCCs, Suezmaxes, Aframaxes, connecting the geological lottery winners with the consumers who depend on their output. The maritime supply chain, the ships, the terminals, the pipelines, the storage facilities, is the physical bridge between a Jurassic plankton bloom and the fuel in your car. Understanding how oil was made, where it is found, and how it is valued is not academic. It is the foundation of everything we discuss on this channel: freight rates, choke point dynamics, trading strategies, and the economics that decide who profits and who pays. This is only chapter 1. The story of crude oil is not complete until you understand how we find it, how we drill for it, how we extract it, how we transport it, how we refine it, and how we value it. In the next episode, we go into the field, literally, to understand how petroleum geologists and geophysicists locate oil deposits thousands of meters beneath the surface without ever seeing them. Seismic surveys, gravity readings, magnetic mapping, and the multi-billion-dollar decisions that rest on their interpretations. This is CRUDE, a SeaMayors documentary series. Episode 2 arrives next week. If this deep dive added value to your understanding, subscribe and turn on notifications. Drop your thoughts in the comments, especially if you work in exploration, geology, or the upstream sector. What did I miss? What do you see in the field that the textbooks never capture? The conversation continues in the comments. See you in episode 2.